I'm very happy today to welcome John Shelf, who's a staff scientist at LBL and head of the Advanced Technologies Group. And John is going to be talking about one project in particular, Cactus, but there are a lot of others similar to it, which are frameworks for doing high-performance computing, which hide all the parallelism from you and let you write in a much higher-level language. Needless to say, you've discovered that might be a useful thing from having written many low-level parallel programs this semester, and so many other people welcome these frameworks to work on. So, John.
All right, thanks. So I may be a bit rusty. I didn't on this, but we'll see. So all right. So the background for this is why do we even get started talking about frameworks? Shouldn't we just have a parallel language, or doesn't that solve all of our problems? Well, the issue is that application code complexity has grown substantially. I mean, the kinds of HPC codes that are in the leading edge are these big science codes. It's like when they build the Large Hadron Collider in CERN. There's hundreds of authors on these papers to develop those particle accelerators. There's now getting to the point that these multidisciplinary, multi-institutional, multinational codes to do the kind of leading edge big science that on particle accelerators. And so this isn't just particle accelerators and tokamaks. The kind of software development we do for leading edge codes is starting to look like that that kind of complexity of science. So advanced parallel languages are necessary. They make it much easier to write your codes, but they're not sufficient. You need to have higher level organizing constructs to bring together teams of programmers to work productively in these codes. And languages need to work together with these frameworks, as we call them, which are really structured environments for designing future HPC codes. So this is an example of, this is QBox. This was a big hero calculation they did at Livermore for first principles atomic structure. It required a huge effort, many people to contribute to the code, and they're experts in different areas. This guy here, he tunes FFTs and DGEMs. Francois Gigi up here, he's the domain scientist. He doesn't understand anything about tuning FFTs and Blue Gene, and yet you have to have a framework to get all these people to work together productively to build a code of this kind of complexity. So it's not just for particle physics anymore. So this is an example from the group that I used to work with, which is the kinds of multinational collaborations it requires to do leading edge astrophysics codes. So when I first started, and that would be 93 or 95, we had the binary black hole grand challenge, and the most advanced code we had at the time was 2D, but nobody had actually created a full computer simulation of black holes colliding. And so that was the cover of Science magazine, and it required 8 US institutions in 5 years for us to pull it together just to do that. That one calculation, because for 90 years all we had were Meissner's analytic solution to this problem, and so it took us, and so there were no new solutions until we were able to come up with that. We also had the binary neutron star grand challenge, which was 5 US institutions to develop all of the pieces parts for colliding neutron stars. So for example, we had to have general relativity to do the high gravitational fluxes in the middle of this calculation, but also had to add a hydro solver to it. And none of the people in the group I was working with knew anything about hydro at the time. Well, we knew some. We knew what Navier-Stokes was, but we were not experts in building hydro codes. So we had to develop a framework that enabled us to collaborate with people who were experts in hydro and also in chemistry. And then the most recent thing is gamma ray bursts for core collapse supernova. And this happened after I left the group, but this was 10 countries, 12 years, 10 countries, 12 institutions, 5 years. In this code, we have general relativity, hydrodynamics, chemistry, radiation transport, analytic topology. Each of these areas has discipline experts that have very little knowledge of the other areas, but we had to come together to assemble these kinds of complicated codes. So the role of these frameworks and structured software design for this kind of thing is hiding complexity, really using good software engineering. But just to say it's software engineering doesn't quite give justice to the organization and the role that this code artifact has in developing these multi-physics codes. So, the role is to clearly separate the roles and responsibilities of the expert programmers who are doing the low-level infrastructure to make it work well in the computer from your domain experts and scientists who are developing these plug-in modules for things like the GR, the hydro, the radiation transport. So, you've heard in Parlab probably productivity layer versus performance layer. I'll talk about like a 3-layer cake conception of this, but good code structure enables this kind of clear separation. The other thing it does is it defines a social contract between your expert programmers and domain scientists. That's another way to look at it, in that your domain scientists, if left to their own devices, will write very undisciplined code. We refer to as spaghetti code, to be kind. This basically says, we're going to handle, X, we're going to do the MPI. You guys just work in this box, please. And as long as you work in this box, we can all work productively together. So it enforces and facilitates a software engineering discipline, which is a style of programming, so that the code is uniform and readable by multiple people. And it hides complex domain-specific parallel abstractions from your scientists to enable performance. So it enables your people who are experts in MPI to really go to town working in the low-level details without disturbing all of the code that was written by your scientists, the hydro solvers and things like that. You want to keep everybody out of each other's hair. And it allows the users of the code to nominally plug code to a serial plugin. So the guys writing the hydro solver will write a piece of code that operates on the data that it was on this block of data, and then hand it back, and I will take care of the rest. I will handle the parallelism. I will handle a lot of the other constraints for parallel programming. So one of the important things was it enabled us to write our infrastructure in C or C++, whereas our domain scientists prefer Fortran. This kind of software coding discipline enables you to give everybody what they want, the low-level stuff to the programmers that like the low level, and a Fortran interface that's nominally serial to your non-expert programmers. So this is the way that we think of the separation of concerns here for frameworks. It's really trying to factor out the different roles of programmers by their area of expertise. So this Einstein-Elvis-Mort thing comes from Microsoft. Einsteins are experts. The Elvises can dance, so they're conversant in that area, but they're not experts in it. And your Morts are novices, and you really don't want Mort to be working in an area that they're non-experts. They'll just mess everything up. And in an old conception of undisciplined programming, everybody, your application scientist tries to do all of this stuff, and bad things happen when you do that. So the layers in the layer cake here are your application scientists, the ones that are really trying to solve the GR problem. They assemble together, like the hydro and the GR, an elliptic solver, in order to do that binary neutron star collision. They are experts in all of the idiosyncrasies of that astrophysics science discipline that they're working in. And they can speak conversantly with people who work in the solvers and algorithm space. So in the solver space, this is where you people who are experts, kind of applied mathematicians, who implement, we had in Cactus, we had about 8 different elliptic solvers because we had different people contributed elliptic solvers that had different properties to them. We had 5 multi-grid elliptic solvers. We had a plug-in for PETSI, and different hydrodynamic solvers. So your solver writers are conversant with your domain scientists, and they also have to understand some of the low-level stuff about the machine architecture to create an efficient algorithm efficient solver. But you wouldn't really want your solver developers, your applied mathematicians, to really be writing stuff for the astrophysics journal. I mean, AppJ. It's just not. Some of them do that, but it's rare a case. And then down at the lower level, we call it the driver layer writers. This is where you implement your idiom for parallelism. These people are experts in the hardware architecture. They might learn a few words by osmosis that these guys use to talk about it. You know, I say GR, but I did not study or practice, Einstein's equations. So this is kind of the area where I used to work. And so you kind of implement an idiom for parallelism, and you manage all of the data allocation and placement on a parallel machine, and you provide an API or an interface so that your solver people have a nice way to express the things that they need to manage parallelism data layout. And by the time you get up here to the application writers, you've completely hidden all the nasty guts that are happening down here. And so this is your layer cake and the separation of developer expertise. And this is a specific example for our user developer roles for real code. And so our application scientist, they want to do a neutron star simulation. So to put it together, they combine together our GR solver, Method Aligns integrator. Valencia group made the Hydro solver for that particular code. And Carpet was AMR driver written by Eric Schneider. And then they have a parameter file that expresses all of the different parameters that are important for trying out different cases of neutron star collisions. And so the framework provides a very high-level assembly for these things, not assembly language. I mean, you can actually just say a thorn list and say, I want these solvers, just put them together, and all of the lower level part, the driver part, will assemble those and execute them in the correct order and do all the parallelism. The solver guys, we had like the PETSI elliptic solver, BAM elliptic solver. John Towns wrote his own custom by CG stab implementation in Fortran. They can, you go from up here where they say, I just want to have them to here, where you get a menu of different choices for implementation that have different performance characteristics, both in terms of convergence and other things. And then down at the lower level here, this is where we implement our idiom for parallelism. So we have Carpet, we had a Samurai AMR driver, Grace, never quite worked, but that's all right, AMR driver, Pug, which was our original Unigrid driver, and Schmug, which was a SMP driver when people still used SGIs, which unfortunately they don't anymore. So that's kind of shows you the, and so at the driver layer, we're handling boundary exchange for your structured grid, and the middle layer here, we're, conceptually, we're just solving elliptic equations. But there's so many different ways to solve it. So, the point here is that these structures, these frameworks, and the software infrastructure behind them enable computer scientists and computational scientists to work together productively. Before we had our framework in Cactus case, at least, we used to have arguments about C++ versus Fortran. It's unnecessary. The people who write solvers really do like to have three-dimensional arrays as first-class citizens, and the people who are manipulating pointer trees would prefer to have an elegant way to express pointers and linked lists, which Fortran, even Fortran 90, does not offer. The other part with the frameworks is they're very modularized. I told you about the thorns that you plug in. These modular structures enable easy unit testing.
Question?
Yes?
You'll tell us what thorns are later.
Oh, sorry. Yes, I will tell you what thorns are. I should back up. We'll just call them modules for now. So if I say thorn, just sub s/sub thorn /module. When we first started with this group, we were actually using RCS, which was a good thing to have any revision control at all. But the problem was that somebody would modify some line of code somewhere, and the domain scientist would say, "Oh my God, it's not producing the right result anymore," and there would be a week of finger pointing. who damaged the code, and then trying to figure out how to back out that change. That's what happens if you don't have unit testing, particularly with these large, complex, multidisciplinary codes. So if you can have each of the solvers in your code easy to unplug and plug in the old version, unplug and plug in the new version, then it enables you to quickly identify where the error crept in, and also quickly evaluate whether a computer science optimization, for example, in the code was beneficial or not. Because you can always go back, you can isolate what the contribution is for each item in the code. And so now our computer jocks and our domain scientists can actually get along together. There was a time that scientists write code and they seem to we always had this complaint that the scientists really were adverse to any new features in codes. If we computer scientists ever made any change to the code, it would take us a long time. So they'd give us a snapshot of the code, we'd make a change, and then when we gave it back to the scientists, they'd say, well, it's been touched by computer scientists. We're pretty sure the numerics are flawed now. And they wouldn't use it. And on the other hand, the computer jocks would write really amazing code, do things like remote steering and parallel I/O systems and much more efficient communication, and yet they would damage the numerics. And in this kind of isolation, this kind of unit testing, separates out their contributions and also enables us to validate each of their contributions separately. So the other thing is advanced CS features become, once you create this modular environment, advanced computer scientists develop features can become instantly accessible to your application scientists. And now you can, instead of trying to train them in the complexity of the code that you wrote, you could just offer them the feature, and then they're interested in the service even though they don't need to know anything about the implementation. And so in the case of Cactus, you just add another item to that list of modules I was telling you about, and it'll be like Cactus web server. And they instantly get access to a web server to monitor their code without actually understanding any of the details of how it was done. And that wasn't true for our old codes. So this is the plugins method, and it also enables us to share physics modules among our computational scientists, which has a benefit. So now we can have 5 different elliptic solvers or multiple different GR solvers to choose from. But as I was talking with Brian about, it also enables you to be ripped off because of the magic of open source. But so be it. You win some and you lose some when it comes to collaborating in software design. So want to differentiate libraries versus frameworks. In a library paradigm, it's a user program invokes the library, so it's an imperative execution model. That means that the library is stuck with however the user laid out the data, and it's invoked when the user decides to invoke it. That's an imperative model. So that gives sometimes the compiler in the system very limited freedom to reorganize or match the physical topology or arrangement of the underlying physical hardware. Your choice of data structures will have and how they're laid out will have a significant effect on the efficiency of the system. So a framework, you don't own main. In a framework, the framework invokes a user plugin, a nominally serial plugin. And that plugin only operates on the data that it's given, and this is known as a declarative execution model. And the scope of side effects for that module are well defined. If you promise you're only going to operate on the data that you were handed, then you get a lot of information about what order is legal to schedule the operations, and it gives you more options for parallelism. And if you really think about it, this is really functional semantics. In the same notion as functional languages, but it's relaxed because inside of any module you're writing Fortran or C code, but external to that module, all of the semantics for invoking that module are the same as the semantics you'd use for functional language like Prolog or Sisal, if anybody can remember Sisal. This is from a DARPA group that we had in 2006 or something, and it was basically came up with a taxonomy for frameworks. So there's the issue with frameworks, there's no one way to do this. And so we created a taxonomy based on how well things are coupled. So this is no component interoperability where you'll have a fluid solver, acoustic solver, structures, electromagnetics. They're all standalone codes. In the physics in industry, so like when Boeing does aircraft or when Procter & Gamble tries to design a new diaper, they're interested in the acoustics of how they crinkle, but they're also interested in fluids for their water absorbent capability, and they have to have a structures code in order to deal with the deformation of the diaper, let's say. And so if you use a physics, these kinds of codes in industry, they're coupled actually through data files. So the structure solver will write out its current state. It'll be read in by the acoustic solver, which will do a step, which will write it back out again, and then the fluid solver, and it does this round robin of being independent codes that exchange information through common file formats. So that's a very shallow component interoperability. But they do this because everybody wants to own their own data structures, and they don't want anybody to see inside of their code. If you want to have a tighter amount of interoperability, you have to give up control of your data structures. You have to have the guys writing the acoustics codes, the structure code, the fluids code, have to agree. And that's the hardest thing with writing frameworks. They have to sit down at a table and agree to a common set of data structures, and if you do, and also mechanisms for invoking those data structures. And that's actually the hardest thing. It's not actually writing the code for a framework that's hard. Once you actually hammer out an agreement on what the data structures look like, writing the code ends up being pretty easy. Getting a bunch of physicists and mathematicians and computer scientists to agree on data structures is by far the most difficult challenge in writing a successful framework. There's one step beyond this that I didn't include, but there's fully coupled models where you have a monster-sized matrix that you solve. But we decided I'm not going to go into that. So this is what an operator split method, they'd say, but doing one time step, you just do a common loop here, and you do one time step of each of these in time.
So, question on the shallow one.
Yeah.
Is there actually disk I/O, and is that what you meant? That they actually write out files
so
in between each call?
they got all sophisticated on us. They M-mapped a file into memory to speed it up. Okay. But initially it was just disk I/O, and then disk I/O got particularly challenging. So they improved it by enabling all of the software infrastructure to remain the same, but that they used a lot of DRAM. But they're all scared senseless, by the way, because they realize that DRAM now is extraordinarily expensive in terms of power and cost, and that design choice is no longer durable for the future. So MST is looking for... All right, so frameworks, domain-specific languages, they enforce coding conventions for big software teams, encapsulate domain-specific idiom for parallelism, create familiar semantics for your domain experts to make them more productive, so it lets them use Fortran, and it creates a clear separation of concerns that lets your computer scientists work in the low-level stuff without disturbing the domain scientists. And that's the thing that I had in the previous page was, so the DARPA Ogden Frameworks meeting, we also have regular meetings at the SIAM CSE, and we had a meeting series called Comp Frame for many years to talk about this, and everybody had a completely different idea about what everybody had framework wars, use my framework, but all of us, in all of our frameworks, it was a surprising concurrence across everybody's framework that we agreed that that all of us gave up main. That was one of the design principles. So these are the durable design principles that work across all these different disparate frameworks. So give up main and let the schedule of parallelism be controlled by the framework. You have stateless plugins. So you, for like a PDE solvers and block structured grid, you invoke your Hydro solver, it operates in what it was told, and it's told what the patch size is, and then it returns. So stateless plugins that only operate what was passed into it, and bounded, well-understood side effects for those plugins. So the plugins can't carry state from invocation to invocation. They only operate in what they were given, and they only touch what was passed to it. And these design principles were common across many different frameworks, which is surprising given how little we agreed about otherwise. All right, so here's our first set of, so we're going to go through 3 examples here. The first is Cactus, which is the code that I used to work on. So I was one of the first 4 developers of Cactus, and now it's almost 20 years. We had our 20-year anniversary now. So I haven't updated this slide in a while. So Cactus was invented, so it's not 20 years, but anyways, it's more than 14 now. We started at the Albert Einstein Institute in 1997 to solve quote-unquote thorny problems in general relativity. Actually, all of the thorniness was amongst the developers who were sharpening knives to kill each other at one point, and so it forced us to sit down and come up with a common agreement. So it's a framework for, it started as a framework for general relativity, but eventually became a framework for HPC, because it really is useful across many different problems that involve PDEs and block structured grids. We use managed increased complexity with high-level abstractions and abstractions for parallelism, and we have an active user community that is not almost 15 years old now. It's and we have about 100 or 150 users or so, I guess, and so it enables us to have collaborative development and or just structured programming. Why is it important to answer this question? That was, I was answering somebody else's, in real time. I like to write slides just before something. I should have removed that. So that's these are the contributors to Cactus, or our current user community. So for GR, where we started, we obviously have a lot more users, but for astrophysics, Zeus MP, so Mike Norman's now director of the San Diego Supercomputing Center, but we had MHD, Hydro, computational fluid dynamics, chemistry, and bioinformatics. So, some of those features are that we have a scalable idiom for parallelism that has actually we've been able to keep it moving forward through many years without rewriting the physics modules. So it's very simple idiom for parallelism. It's parallel boundary exchange for block structured grids, which everybody's familiar with. And we give our algorithm developers the serial plugins, and they're shielded from the complexity of our parallelism implementation. There's another framework called Neuron, which is for neurodynamic simulations, and it was actually the guy who developed that where I got this term idiom for parallelism, because they basically came up with, when they have events, the simulation, they kept on tripping over each other trying to figure out how to express that in parallel. And once they came up with a common idiom for expressing these impulses and the connections between the neurons, then suddenly everything fell into place. They were able to develop an API. Different people could develop different neuron models and plug it in without understanding how the framework managed the parallelism. And so that's the magic of the idiom for parallelism. It's kind of like the dwarves. And once you figure out a good recipe for managing the information flow and scheduling for a parallel machine, then you can reuse that for a broad variety of problems. So the other part of Cactus, and this is part of for services, so framework isn't just about managing the parallelism and doing the plugins. Framework also often provides services like a build system. So we had a lot of errors in make files, so we created a lot of automation to automatically generate the make files and keep it out of the user's way. And it also includes known architectures to store our accumulated wisdom about idiosyncrasies of different compilers. It has also modular application composition system. So rather than the old way was you'd have the main in your code and you'd pound define in or undefine different code components that you wanted to include, or you just basically write code with a text editor. Here we just provide the list of the modules and it self-assembles the modules in the correct order according to a set of constraints that we provide. And so that's also been very useful, and it also includes automated unit testing. I forgot to mention also the build system is that we made it so that you could build on your laptop, test your results, and then take the same code, throw it on the supercomputer, rebuild, it reconfigures itself, knowing that it's on a parallel machine.
Could you just say what V&V means?
Verification and validation. Yes. So we have a way, one of the other things that happens is you'll make a minor change in the code or a change in compiler and you won't get the same numerical answer that you got last time. And it may be it's okay, maybe it isn't. We came up with a way to automatically capture for any given module, given a set of inputs, what outputs it produced on the previous machine or the previous version of that module. When you made any change to it, it would automatically set up a testing harness for that one module to determine whether or not it gets the same answer. And so whenever you try to check something new into the system, it would run it through this V&V validation test or verification test. The validation is a longer thing, and so we have to go against an analytic model for that. But anyways, that's what that was about. And then lastly, our framework supports language neutrality by enabling people to write their modules in different languages, and it automatically generates the bindings and fixes them up so that you don't have to worry about which language you're writing in. We're tired of religious battles. So our terminology is that we have flesh, which is the services or the glue, that build system, the parameter file generator, all these things that bring our component in architecture together. It used to be that the flesh, when Cactus used to have a fat flesh, hence the name Cactus, and we had little thorns plugged in around the side. And over the years, we started taking more and more things and factoring them out into modules themselves, including the idiom for parallelism. And now we should probably call it rows because the flesh is a very small amount of code now, and everything is a module. But when we started, it was a cactus. The driver, those are the things that implement our idiom for parallelism. So it implements our Dorf-specific data types, if you may. It handles data allocation, placement, and the domain decomposition. And each of these features are in their own module. And then it implements the communication pattern necessary to implement that idiom for parallelism. And it implements thread scheduling, thread creation, and all the other things we need to implement our parallelism. And then the thorn. And so a thorn is, it used to be that thorns were only for implementing solvers. And that was that serial invoked plugin that I was telling you about earlier. It's been generalized in more recent versions so that it's solver or a service. So everything from web servers, I/O, even the idiom for parallelism now is packaged into a thorn so that it's modular. So we have our hardware abstraction layer, the flesh, which is the binding that brings the modules here at the highest level.
And question?
Yep.
So how does this map to the three layers of?
Yes. So the thorn, it's not an exact mapping anymore. So it used to be a clean mapping in that the thorn used to be the highest layer, and that the driver was the lowest layer. And in fact, thorn wasn't really, the thorn's really the solver's layer, and then we gave a composition environment, the flesh, that enabled a domain scientist to just give a list of thorns and assemble them together into an application. The thorn, because it also is a component, implements our modularizes our computer science things that happen at the bottom layer. It's really now become just a description of the ability to modularize a complicated code. So it includes both the lowest level and the highest level now. It supports that three-layer cake, but it isn't itself the three-layer cake. All right, so Cactus obviously is not the only framework in the world. It just happened to be the framework that I was working on. And so regulars at our meetings to talk about frameworks are people from Neuron, which was parallel implementation of Genesis, neurodynamic simulation, which is developed here at Berkeley. Genesis was, Bower Lab. Sierra, it's a finite element structural mechanics code from Sandia, so a completely different problem area. UPIC and TechX, these are framework. UPIC was developed at UCLA. TechX has something called Vorpal. These are frameworks for developing particle and cell codes. They're very modular, they do all sorts of stuff. They do fusion and particle accelerator simulations that use particle and cell method. You have Chombo, which Brian here is lead developer on, I guess. And again, common feature is that the model of computation is well understood and broadly used. So, this is that idiom for parallelism. We were doing boundary exchange years before we developed a framework to implement that as an idiom. And the key is that we found that there's many different ways you could parallelize a PDE solver and block structure grid, including people who go crazy and do these point-wise parallel things that are very slow. But once you have a broadly agreed upon idiom for parallelism, now, once it's well understood what the API is to express that well understood paradigm, and so that's another common feature is each of these people had worked out what's the best way to implement the parallelism, and then the framework ended up just encoding that in an API. Common benefits and motivations for this stuff though are the modularity, the segmentation of expertise, unit testing, ability to support performance, more robust performance analysis, correctness testing, and reuse of solver components. Any component that's only used once, well, you have to ask the question, why did I bother to make a component? Reusability means that you thought ahead to all the different possible uses of that. And so this is our, our black hole stuff. The real reason why we have the Cactus code, the whole reason the group exists is that they've built these giant gravitational wave detectors like LIGO and Virgo. They have these 4-kilometer long arms here that are laser interferometers to try to detect gravitational waves, which should elongate those arms a little bit. About a tenth the width of a hydrogen atom, though, is how small of a movement in those arms needs to be detectable. So they need to develop filtering software to filter out trucks and nearby highways and things like that. So we know that when these black holes collide, they in-spiral, and it creates gravitational waves. And when they merge, they create this big ring. And it's like a bell when you actually play it at full speed. And so actually understanding the characteristics, this characteristic ring enables us to develop software to actually enable these detectors to detect it in an extremely noisy environment. And so this is pretty pictures for everybody for all our black hole collision stuff. So these are gravitational waves. So this is the first one I'd worked on. This was This is on a CM5, and we also did this in a CM5, and these are the waves propagating away from a merged black hole that's here in the center. And then this is Werner Benger, so this is after I left, and this is volume rendering of 3D gravitational waves propagating out. Yeah?
Can you go back to the last slide? You had a 0.01 second was for the merger?
Yes.
That it happens like on a 0.01 second time scale?
Yeah. Yeah, it's very fast. Okay. And so they will do, the black holes will dance around each other for a good long time. And that's one of the things actually we discovered in this simulation here was this 40-second, this diagram is wrong actually because it was done, we did this 15 years ago. What we discovered is that the reason why the black holes would actually even come together at all is that they are dissipating energy through gravitational radiation. The analytic model for that initial condition was thought to be correct for about 30 years. And then we ran the first simulations of a full 3D in-spiral on the NERSC system when it was the second largest machine in the world. So, and discovered that the black holes were coming in together quicker than we had expected. It didn't make any sense. So we thought that our code was wrong. And it took 5 years to discover actually that the initial conditions were wrong. So this Moudon equations that had stood for 30 years, turned out there was a flaw in their reasoning. And so we discovered it using the code. And so it dissipates more energy than was anticipated. And so now we can correctly set up. We can't simulate this amount of time would take us like a decade to simulate 40 seconds. So we boosted the black holes based on the initial conditions that the Moudon equations told us, and to simulate this 0.1 second period, 0.01 second period, which took a week on the second largest machine on the planet, and what we discovered was that the Moudon equations were wrong, and so it's an interesting side story about how numerical science can discover things that are inaccessible to pure theory. Okay, so we'll just talk about how Cactus works, and then I'm going to walk through some examples from other frameworks, just so that it's not all Cactus all the time. So this is the scalar wave equation in 3D. So it's got time and then the x, y, z components for the wave equation. This is an initial value problem. So analytically, you would think of it as a wave equation. You have a wave and it propagates in time and it might attenuate some, but that's what the scalar wave equation in 3D is describing. It's describing this spatial, the spatial values, and the fact that as you step in time, it will propagate. So now we convert from the purely, we have to discretize this wave equation because we can't represent continuous functions on these machines. And discretization is basically chopping that equation up into little pieces and using the method of finite differences to express that wave function in 3D. So this is centered second order wave equation. So for time step n+1 in directions I, j, and k, we have this PDE that describes how I evolve forward, that this point, based on the values of its neighbors and the size of this time step, where it's going to be in the next time step, or what its value will be in the next time step. So that's our applying a finite difference numerical method to this. And so now we go and we're going to put this into this is looking at it in 1D, but really we're going to allocate some memory, a 2D or 3D block of memory, We're going to lay that initial condition for the wave equation out onto that grid and apply some boundary conditions. And so your framework needs to, you need to express what the grid spacing is, so how big these cells are, what the time step size is, what are the coordinates, what's your initial data to lay that problem out in the grid. So we usually use an input deck or a parameter file to describe those parameters for setting up your problem. So a simple problem, it's got an analytic solution, but I'm just stepping through this to show all of the features that you use to start up, bootstrap one of these problems in 3D. So, this is an example of the old school way that we would write this. This is a Fortran code, main.f. It's not that bad. I'm sorry that some people are like, oh my God, it's Fortran. I set up my coordinate system here. So this is dimension arrays for the coordinate system. The number of points in this problem is 30, and this is in each dimension. This is, let's see here, is this my, okay, initializing the array here, open some output files. So call initial data basically initializes this grid with some initial values, and then call output to open up my files, and then I evolve. So I do for iteration 1 to the number of time steps, I call evolve, and evolve is essentially applying that PDE solver, the stencil, to each of the points in this code. And so the standalone serial program, you'll be able to do a nice plot of the wave equation 3D, oscillating around. So that's the serial version of this. Now, if I want to convert that serial program into a thorn, that is not a Cactus module. What's going on here? There we go. I extract out just this piece right here, and I package it into, and I get rid of all this other crap because everything else in here is just boilerplate for setting up the code. I throw away all the rest of the stuff, and I get my parallelism and modularity by packaging up just the central computation into its own unit. Oh boy, I removed too many slides, unfortunately. I decided my presentation last year was too long, and that didn't work the way I expected it to. All right. So anyways, I eliminated the part that explained how we then take that module and make it parallel, but we might get back to that in a later slide, and it may magically reappear. All right, so here are like the steps. So some of the things that you need to define in order to do that that little module here. One thing that you need to define is the schedule. So when is it legal to run that little module that I separated out? And so we actually have some standard named bins for the schedule. So startup, which is allocating arrays, initial, which is initializing the arrays to their initial values, pre-step, evolution, post-step, analysis, output. So each of these are bins that could be part of this iteration when I'm doing time steps, and then the cleanup for the termination part. So for any given module that I define, I tell it that I'm going to schedule it as at evolve. So I'm saying that you will invoke this plugin and during that evolve bin. The language for that this module that I created is Fortran, and this scalar evolve is a variable that is going to be involved in parallel communication. So it needs to be you need to track it and synchronize it. And then it has this little annotation here so that when you ask the code, what were you doing, we can actually have full text to explain what it was doing in that evolution bin rather than just giving you the name of the subroutine call, which is scalar evolve. So scalar evolve is the name of the subroutine call that's being invoked. The other thing is param.ccl. So I told you about the parameters like the delta t, the time step size, the grid spacing. So we created a meta language to describe different parameter definitions. So like real, radius, then it has a name for that. So if you ask it, what is this variable, it'll tell you, it'll have a short description of what it is. And then its legal values are 0 to infinity, essentially. And the radius has to be positive, so we don't allow negative radiuses, and it'll flag an error if you try to go below 0. So this is the boundaries, and its initial value is 0.0, its default value. So the parameter file, if you have, it'll read the parameter file in. The default value, if you don't change anything, will be 0. But if you do change it, you say parameter radius equals blah, whatever value you want it to be. Yeah.
Could you say briefly what remote steering is?
Sure. I'll actually have a unit on remote steering later, I think. Remote steering is while your code is running, you can change these variables. So initially, we just had this so that you could have a standard input file to describe all of the parameters in the problem that need to be defined to set up a complicated problem. We found that sometimes you do your parameters wrong and the simulation go awry. So the remote steering enabled us to connect with a web browser and see how the simulation was going. And if something bad happened, you could change the parameters and click restart, and it would send the simulation back to the beginning with a new set of parameters so you could actually dynamically steer the computation. We initially had ideas that we would actually steer things while it was running and forward stepping. It turns out to be a stupid idea. But being able to restart the calculation while it's running is very beneficial. So here's an example for our wave toy. This is a more complicated parameter, so the different boundary conditions to use. And so in addition to floating point values in the parameter file, you can also define a keyword for different kinds of boundary conditions that you can select in the parameter file. And so this is the language, the meta language used to describe different items for a parameter file. So whenever you write a subroutine call, instead of it just being a subroutine call, you have these additional information about when it's legal to schedule it and also what parameters that subroutine call would need. And it enables you to then have a nice textual parameter file to define these parameters as a runtime thing. So that time is a floating point value. DTFAC, which is one of the subroutine calls, is watching it, and we're defining basically all those parameters that are needed by different subroutine calls in the code, or different modules of the code. So this is kind of object-oriented, so it's the QFT is the package, and then this is the parameter name. The elliptic solver would be like elliptic : : and then whatever parameters the elliptic solver needs to know about. Here's a thorn list. So I told you about for our scientists, we give them an easy way to assemble the code for full applications. So in order to, it used to be that you'd actually have to edit Fortran code in order to do this. We just created an externalized text file that has just a list of the necessary components that you need to assemble these codes. And it'll automatically, since each of these subroutines has its description of when it's legal to schedule it, they'll self-assemble into the correct order. So I can put these into a file in any order, and it'll automatically resolve the constraints, the scheduling constraints, and execute them in the order that's legal. And in addition, it will add in any of the parameters that were required for each of these modules will instantly become available in the parameter file. And so all I have to do is list the set of things I need. So I need boundary conditions. I need a 3D Cartesian grid. I want some I/O, some basic I/O. I need a time stepping. I want the initial data for the scalar wave equation. I need to have the thing that actually evolves the scalar wave equation, and I have PUG, which is my parallel unigrid driver, which implements my MPI. So I just it's like a Chinese menu here. I just take the menu of things that I need for my code, I throw them into a file, and it'll assemble them. They'll all come out in the right order. So this is the missing slide about the next step for our parallelization process. I rediscovered it. So our central idiom for parallelism is to domain decompose these grids, and then you take a stencil and you sweep it across the grid, and the stencil looks at the nearest neighbors and updates the grid point. The problem is that when you get to the edges here, you don't want to do an expensive communication to a non-local processor in order to capture the stencil, the guy at the end. So what you do instead is you replicate the boundaries. You create a ghost cell. And so instead of going all the way to the end and having a dangling partner here, you just go up one short of the end and you get your neighbor, which is a duplicate of this guy over here. And then after you update all the grid points, you do a boundary exchange, and you take all of those values that are in this ghost region and you exchange them en masse. And this is much, much more efficient than referencing those points individually. And everybody does it. I mean, it's not like we invented this. But what we did do is we packaged it in a way that now all you have to do is say, well, it used to be in our older codes, the G code, you'd call sync grids. So you'd have a loop, and then you'd call sync grids, and it would update the boundary conditions for that grid. Now that we have this modular system for composing these things, we've been able to even hide the sync grids. So it can just see that this grid has been updated by my module. It says that I've updated the grid, and it'll automatically then invoke MPI behind your back to synchronize things. Yeah.
One of the optimizations we talked about earlier was, say, exchanging 3 ghost zones all at once. So
right.
You could take 3 steps, and is that all?
Yeah, I got
available?
so yeah. So yeah, that'll be a good foreshadowing. So anyways, so this is our boundary exchange. We represent it as a standard. So all of the rules that we have and the data structures that we defined, you get this MPI boundary exchange stuff for free. Moreover, it so happens that if you respect that boundary exchange interface, you can also do AMR. Yes?
The sync grids operation, is it like a standard operation?
Yes. So because... Yeah, is the sync grids operation a standard operation? And the answer is we've been, by formalizing the data structures and the calling interfaces, we're able to make that a standard operation so that nobody has to rewrite it for any new codes are developed. You write a serial plugin, and then sync grids handles all of this stuff transparently for you. And that's why it's important to hammer out agreements on data structures, things like that. That's the benefits of formalizing interfaces. But you have to give up control of the data structures in order to get that kind of interoperation. So people always complain that MPI is too low level and it's terrible and all this stuff. The fact of the matter is, when you can hide MPI behind sync grids, nobody cares if you use MPI or anything else, actually. So we found that by the data structures that we'd used to in this plugin architecture, by using those very same data structures and hiding some initial data, we could also do AMR, which is adaptive mesh refinement, which I'll talk about some more in the Chambo part of this talk. And in fact, this paradigm, this idiom for parallelization, is so robust that we were able to use plug in different frameworks for, different packages for implementing the AMR grid implementation, doing the AMR time stepping. And that's about the time that we modularized also the driver part of the structures. Should enable you to adopt different people's packages to implement the low-level details for your communication and data allocation. So here's our application. So we took that block of code that I had embedded in Fortran, and I gave it a param.ccl file and a schedule constraints. and when I plug it into the Thorn list here, so let's hear activating Thorn hello world. Okay, wrong Thorn here, but anyways, then you trivially get a parallel application. So I have the same set of code that I had dropped into the Fortran. It was actually less code, and the framework takes care of all the rest to parallelize the code. So once you have a framework, there's a lot of really cool stuff you can do. So one thing that abstractions that these frameworks give you is it enables auto-tuning. So normally if you write a monolithic piece of Fortran code, if you want to tune it, then you're just modifying all the lines of the code in that file. And then tuning has a tendency to, obfuscate your code to the point that it becomes unusable. And so what you'd like to do is enable the frameworks to automatically tune for performance. And so here's an example from a Gordon Bell thing we did a long time ago now because it uses an Origin 2000. And so we had a IBM SP system connected to an SGI Origin over a wide area network, OC12 network, and you'd think that that would really destroy performance. But in fact, what we determined is that the bandwidth isn't the limiting factor for these wide area distributed experiments. It's really the latency that kills. So we were getting like 15% scaling efficiency, and it was really quite terrible. But we thought by linking multiple machines together, we could get more memory, and that was kind of what we were after. So what we do is take that driver layer, the PUG, and modified it so that it could ghost cells on demand. And when it does this, it's doing it at the low-level layer, but because the user's code, the thing that's doing the GR equations, isn't responsible for allocating the memory and it isn't responsible for the communication, we could dynamically add ghost zones to the PDE grids, and it doesn't know that it happened. So the physicists didn't have to change any of their solver modules for us to be able to do this kind of adaptation. So we have sucky performance, it adds 2 ghost zones, and then it takes another time step. It sees that it improved performance, so now it adds 3 ghost zones. And that further improves performance. And then it sees that by adding 4 ghost zones, it doesn't really improve things, so it quits adding ghost zones. And then it tries data compression. So we could hide in the low-level computer science layers of this application, hide the automatic addition and optimization of the number of ghost cells used in the computation, and also hide more sophisticated things like different compression methods. So there are like 3 different compression methods solved. And it enables us to adapt intelligently to the conditions of the machine. And again, no changes needed to be made to any of the physics or solver components. The only thing that changed was that PUG layer, the lowest level driver layer. Here's another example is that we used Cactus to implement what today they call MapReduce, I guess. We called it a task farming driver. It was for solving for really large genomics calculation. It was really running sequence matching for SC2002, yeah. So it basically would send out subtasks to lots of different machines all over the place. We could use a web page to monitor its progress and see if there were particular directions that we wanted to steer the job. But more importantly, it would always keep track of these machines, and a machine could fail, and it would just move the work somewhere else dynamically. So it keep track of all these things. Another example is that I told you that the scientists' thorns or components don't only operate in the data that they're invoked, and that the framework allocates the data. You also saw that when we declared all of the data arrays and all of the parameters, that we named each of those and said what the data type is. That means that that information is available to the framework to take care of. When the framework has all that information, it can automatically manage checkpoint and restarts. And in this case, this is an example where we took advantage of this checkpointing feature. So the code was running at UC, And then performance starts taking a dive, and so so we applied a load. This was using something kind of like Berkeley Boink. It was called Condor. So if somebody starts running on your Condor machine, then your performance will start tanking really fast. So after it violates its contract, the expected performance several times, it decides to checkpoint itself. And then it looks around on the network for a new machine to move itself to. It FTPs itself to that machine and then restarts on a different machine elsewhere at UC. So this is an example of all the extra introspection you get from a framework can enable you to implement these kind of nomadic codes.
Question?
Yep.
So clouds have similar motivations and perhaps solutions. So,
Yeah.
But obviously your system has a lot of other features. So I don't know if you can comment on the pros and cons of when you'd use one infrastructure versus another.
Yeah, the cloud, so this was basically, Condor was scavenging cycles and machines in your department, for example. And clouds are leasing time on a machine elsewhere. Condor had the advantage of it was machines in your department, so they're quote unquote free. The cloud model does charge for the resource. I think that this same infrastructure would work in both cases where you are trying to grab as many cycles as are available at any given time. So this very same nomadic application thing might actually make sense in the cloud, because one of the things that we found in the Amazon cloud was it's not dynamically infinitely elastic. We would try to start a job and you might wait 8 hours to accumulate enough processors to begin your job. In the meantime, you get charged for the ones that you've scavenged thus far. This would enable you to start up your application, and as more resources come available, you can dynamically expand the application to use more resources. So I'll move on. So this is remote steering and visualization. We created a plugin. I told you about the introspection enables us to do checkpointing. The introspection also enables you to modify parameters and variables while the code is running, and also to remotely visualize the current progress and data arrays. So we can take and pull from the code while it's running a snapshot of the 3D array, one of the 3D arrays that we're interested in, and do remote visualization of that data. We had everything from web browsers to, you can go to the Cactus webpage and do this for yourself. But we wrote our own, it's not a real Apache web server, but your web browser thinks it's a web server. We wrote a plug into the code so you can connect to the code while it's running on a supercomputer and monitor its progress and change variables. In fact, we got very sophisticated with defining a standard interface to do remote steering that actually got adopted by Intel for its remote steering product, and so Intel still uses it, and for one of its experiments. So remote steering is essentially remotely connecting and monitoring your job. And so here's an example here where you can see this was the smartphone when we wrote this slide. We can take slices in time of a code while it's running, and it has a list of different active thorns, so we can check and see how every piece is part of your modular code is working. In future directions, they have a CFD toolkit that they're working on. Currently, it's just a teaching tool, but they're experimenting with supporting finite element codes, and this is a cooperation with Sandia National Lab. So, considerations for CS267, you've heard about Phil Colella's 7 dwarfs or the 13 motifs or whatever. You can think of the canonical framework per dwarf, or there's a good thing to look at a literature search and see for each of these dwarves what are the idioms for parallelism that have emerged for each of those things, and what is a effective or efficient way of expressing this in a higher level so that you could create a framework to manage the data structures and manage the parallelism. Because you do it once, you do it all by hand. It's all code. You have to write. You always have to write code at the end of the day. But what are the parts of that code you could formalize so you could reuse it across multiple problems in that domain? It's just an interesting.
When you say framework, you don't mean like a cactus for meshes and a cactus for dense linear algebra, because you'd like to use them all together, right?
Well, no. Initially, you start with a cactus for meshes and a cactus for dense linear algebra, and for that matter, a cactus for particle codes. Coupling has its own set of issues. So, for example, we created a cactus particle and cell extension, and initially, the coupling wasn't as trivial as we originally expected. There was a lot of features that were missing from our block structured grid code that were not important to that code, but were important to PIC codes. And so we created initially a standalone PIC code extension and then determined what we were missing from the block together and reconcile the data structures, let's say. So yes, that would be the target, but I would take it one step at a time, yeah. Grand unification is hard for everybody. So here's some examples from Chombo. Chombo is an AMR code. So this is a lot of slides that from Brian actually. So block structured grid takes the whole PDE solvers and uniform grids that I was talking about in the previous thing to a whole new level where you can actually apply refinement of your grid structures exactly where it's needed. It makes much more efficient, effective use of supercomputers. So the most efficient flop is the one that you don't execute. So don't execute flops where they're not needed. It makes for much more efficient code. So this is a Berger and Oliger and Berger-Colella algorithm. You basically take uniform grids with different resolutions. You basically decide that this is the base grid, and then you flag these cells saying, but actually there's stuff happening here that's A, interesting, B, needs more refinement because I need to have more resolution where something interesting happened. You put it together and you get a patch refinement exactly where it's needed. But these grids remain distinct domains. It isn't actually combining these together. You actually, this combined grid is in fact a combination of a level 0 grid, and then you project values from this grid onto these refined grids at your level 1, and you do steps on that. And then you project those in turn to further levels of refinement. You can do this recursively as deep as you need to go in order to achieve the level of refinement you need to track something that's interesting happening in your code. This is the Chombo conceptualization of the layering of this code. They have layer 1 is just the patches, the operations, the patches themselves and the operations that you're allowed to apply to those patches, so the rectilinear grids. The layer 2 is managing interactions between the different levels of refinement, so that's prolongation, restriction, things like that, averaging. Layer 3 is your solver libraries, so you have layer 1, layer 2 provide you with the semantics for what you can do with those patches. Layer 3 is actually then what kind of algorithm or solver you build using those semantics for describing the AMR operations. And then layer 4 is like Cactus, it's the complete parallel application. So if we want to do the mapping to the layer cake that I was talking about, layer 1 and layer 2 is what we call driver layer stuff. Layer 3 is your the solver library. Well, we have solvers in the Cactus. And then layer 4 is complete applications. That was the top level of my layer cake, which was assembly of complicated codes. And with all frameworks, I think it kind of exists outside of this layer cake is our utility layer, which is your APIs, your I/O, your build system, things like that. So, AMR, one of the things that makes it difficult is it requires very complicated boundary conditions, whereas, the domain decomposition for uniform grid codes, you always have exactly matching abutting grids. Here you might have something where a grid is abutting a coarser grid, or they just won't line up exactly. And so doing the set calculus to calculate what the overlaps are and who you need to exchange with is very involved operation. And it's the kind of code you want to write once and not have to write again for each application. So they create these box tools in order to describe those basic boxes and sets of boxes. So they have the infamous FRA box. That's the lowest level of this. And then you need to, I missed the part where I calculate the intersections, but we'll just go on. You need to deal with layout in a parallel machine. So for example, a conventional layout, you will end up having a lot of the surface to volume ratio is not maximized in terms of the communication of this. If you use Morton ordering layout, then you can actually minimize the surface to volume ratio to actually improve the effectiveness of your communication. This is also a non-trivial thing to calculate, and so it's not something you want your domain scientists calculating how to optimally lay this problem out on a massively parallel machine. You want to create a modular plugin to describe your mechanism, your algorithm for laying out the data on these parallel machines. And you want your ghost zone exchange system then to be able to correctly do the exchanges regardless of what different choices you make for data layout on the machine. So this is where we get into the box layout. So they have methods for managing the boxes and manage which processors they get assigned to, and that you could plug in different approaches to managing that box layout and do it in a way that does not perturb the calculation of the intersections that you need to do your ghost zone updates and things like that. And then the set calculus for managing the exchanges between the boxes. So then the next layer up in this, their layer cake is the stepping routine. This is a very complicated set of tasks that you have to do for each time step in an AMR calculation. So, for each level in this grid, first you have to estimate the error for every single cell in that level, and you flag those cells saying, this cell, the error is going to be too high in a given time step. That's what the error estimator does. So you'll flag it, and then you have to do what's called a clustering algorithm, which decides, given that there's kind of a random noise of flagged cells, you want to try to find a way to circle as many cells that are flagged for refinement as possible and aggregate them into large grids. And you might actually aggregate it with cells that don't need to be refined, but you're trying to balance the efficiency of larger grids with the only putting the box around cells that need to be refined. So you have an error estimator, and so then you use that to decide to create a covering box set that covers as many flagged cells as you can for the next level up in refinement. Then you need to assign those boxes to processors to respect load balancing and also memory balancing. You need to copy, or not really copy, you need to project your current solution to these refined grids. And then you take a forward step, and you have different kind of stepping routines. And then after these guys, this will proceed recursively down to the finest level, but then you'll also need to copy data back, so the restriction operation back to reproject interpolate the data back into your coarser grids. So given all that, you want to have classes that manage this complicated dance that you have to do for the time stepping in AMR. And so that it gets down to, you just say AMR level advance, and all of that scripting of these complicated operations and the prolongation restriction that you define that declaratively. You say, these are the boundary conditions that I want to use. Here's the solvers that I want to invoke on that level. And here are my prolongation restriction operators. And then when you call advance, that it does all that automation for you. And so when people think in terms of abstractions as making things less efficient, more levels of indirection, things like that. But in fact, a well-constructed set of abstractions like this one, where they have boxes, intersections of boxes, and then the time steps, and so on and so forth, actually is your path to improving performance, to the point that this is back when 10,000 was a lot of processors. They can scale now to hundreds of thousands of processors effectively. And so this discipline, this structured approach to programming that you get with a framework actually is used to enforce design rules that enable performance rather than the other way around. So this really isn't reducing performance through more layers of abstraction. It's actually improving performance. At that, am I at the end of this? Yes. Okay. All right. So I'm just going to point out that there's PETSI is for PD is another thing, and you can take a look at the slides in PETSI. It also steps you through the declarative process of saying these are the operations that I want done, but then handing over control to the framework to actually decide what order those operations should occur, and also how the data should be partitioned in an optimal way given the diversity of machine architectures. So I think this is another very elegant framework, and it shows the declarative programming style. So rather than saying, first do this, then do this, then do this, frameworks enable you to adopt this declarative style where you say, these are the things that need to get done, and I'm going to tell you what the constraints are, but you, the framework, you can figure out how to do it. So, all right.
Thank the speaker. Just want to say there's certainly lots more tutorial material online to learn about these frameworks, and if you want to use it for a class project, and of course many of you have already sent me good proposals, but if you want to think about using this is fine as well. So I had one question. When you did those spinning black holes, those were not adaptive meshes?
Yeah, the first version wasn't, but since then they only do it with adaptive meshes. It's completely impossible with the uniform grid. Yep.
Okay.
We had to do a co-moving coordinates. Oh yeah, we had to do a co-moving coordinate system though.